Hi everyone, and welcome back to this video series about using the Python package Turbulucid. So in this episode we're going to go through a bunch of functions which is in the case object. To start with, again in Power View, and what I'm going to do is extract this slice which is not aligned with any coordinate axis, as you see. And what I want you to understand is that when you take out this arbitrary 2D slice, what Turbulucid is going to do is transform it into the XY plane. So basically it will look at the angle of a normal compared to the Z normal and make an appropriate transformation so that it's in the XY plane. So if we go into the notebook here, then we see that I've opened the case. It's called tilted slice. And then I also plotted it. So as we can see, we have a correct representation of the data, but not necessarily optimally presented in terms of, well, the position of the data in the XY plane. You might, for example, want to rotate it so that this edge is aligned with the x-axis. Now there's a couple of things in the case object which can be used to make such transformation. So let's start small. First I want to show you the function called case bounds. And this is very simple. It's just going to tell you, it's going to return a tuple which returns the bounds of the case in the x and y direction. So we have x first, so we can see it's from 0.09 approximately to 0.8, let's say. We see from the graph that seems to be completely correct. And the same with the y-axis, so it's from minus 116 to about minus 0.07. So what can we do with the case geometry? Well, there are three methods which we're going to go through. The first one is translate. And this one is very simple. You just give it two values corresponding to a shift in x and y. So let's just write 1, 1. And then let's write case bounds again. Bounds. So as you can see, they both got shifted by 1, basically. So if we now plot it again, we'll also see it in the plot. Yes. So very simple. The second one is rotate, which is something you might want to use here. And here we give the angle in degrees, corresponding to counterclockwise rotation. So let's try to set minus 30 and see what happens. Yeah, as expected, we rotated 30 degrees clockwise, right? But it's not quite enough, so yeah. But of course, we can play with this, and then we can align this one with the x-axis if we want. So it will need more, maybe, I don't know, 60, something like that. Let's just, for the heck of it, try it. Yeah, a bit too much. Yeah, because that got stacked upon the original 30, of course. So that was definitely too much. All right, so that's translate and rotate, and the last one is scale. And this one's also simple. So also two values, and that's gonna scale the x and y axis by the given values. As with the other scaling functionality, which is in the plot functions, this is going to divide by the values you provide. So if I write in 10, 10, it's going to divide the x and y axis by 10. Yeah, so as you can see, these became smaller by about an order of magnitude. And if we draw this again, we're going to see it's in the plot as well. Yeah. So the reason why do we want to use this if we have, for example, if we look at plot boundaries, we know that we have these scale x, scale y parameters, which are most plotting functions. Well, basically, if we know that we always want to scale the plots or just want to work with the scaled data, this is the way to go, right? You do it once, and then you don't have to use the ones built into the plot functions anymore. Okay, so that is the first four functions which we wanted to go through today. So this is basically manipulating the case geometry, which can be handy. Now, the next section is going to be about working with the data which is stored at the edges and the cells which are adjacent to the edges. So there are two functions for that, respectively boundary data and boundary cell data. For this one, I think I'm going to pick up another case. We're going to look at the periodic hill again. So let's load that. And I'm going to just plot some field here so that we can see the geometry. There we go. That's a periodic hill. Now, let's start with boundary data. And let's look at the docstring. So as we can see, there's two parameters. So one is boundary, which is a string, and the other is sort, which we're going to look at next. But first, let's look at this boundary thing. So that's the name of a boundary. So what does that mean? What are the boundary names? Well, you can look at that by writing case boundaries. And as you can see, for this case, we actually have 4 boundaries defined: bottom wall, top wall, inlet, and outlet. Now, if you extract data from ParaView like this, then you're only going to have one boundary, which is called boundary, corresponding to all the edges, okay? So basically, in that case, perhaps all of this functionality is not very useful, or it's just a bit more difficult to use it. Now, the reason why for the periodic hill I have 4 named boundaries is because this is actually stored in the format native to Turbulucid. And in this case, we have this part of the boundary is top wall, this is bottom wall, and this is inlet and outlet. But anyway, this is available, as I said, even if you just extract data on your own. It's just that you'll have to, if you want to look at a specific part of a boundary, you'll have to sort of filter the data somehow on your own. So let's see what happens if we pass it some boundary name, for example, inlet. If we run this, we're going to get a bunch of data back, and the format of this is very similar to profile along line. Okay, so the first, let's call it P and V. So P is going to hold the points, so that's the edge centers of the boundary. Okay, and V is going to be a dictionary with values of the fields. So if we look at P individually, we see that the x-coordinate is always 0 as expected, and y is sort of going from 0 upwards. And v is a dictionary, so if we run v keys, we see that it contains all the data we want. So now, for example, we can plot, let's take the y values and then v, for example, p mean. So this is the distribution of the pressure over the inlet boundary. So this can be quite handy. For instance, we could take the top boundary and plot CP using this, or the bottom boundary. Now, the function boundary cell data is very, very similar. The only difference is that instead of the values at the edge centers, it's going to grab the values which are in the cell centers of the adjacent cells. Okay, so if we're going to use boundary cell data instead and plot, we're going to get something very similar, I guess, because there's no much significant difference between what's at the edge here and what is in the cells. Okay, so next let's look at dist, normals, and tangents. That's the 3 functions we have left. So dist is a very simple function also. What dist does is also takes a boundary name. For example, let's take top wall maybe. And what it returns is the distance between the cell centers of the wall adjacent cells to the edge centers of the boundary. Okay, so basically that's your distance from the boundary to the wall adjacent cell center. So unlike the boundary data and boundary cell data, it's not an object or not a member of the case object. So here we need to pass the case first. And here we go. So we get the distance and it's more or less constant, right? Okay, so something which we also have in the distance function is a parameter called corrected. And this is best explained with a picture. So this is our boundary, and then this is our cell. Okay, like this. And this is our cell center, and this is our edge center. So if corrected is true, what is going to be returned is this projection. So the actual distance. So usually you want corrected to be true, and by default it is true. If corrected is off, you're instead going to return the raw distance between the cell center and the edge center. Okay, so that's what it does. In this case, it's not going to make any difference because the cells are basically orthogonal. All right, let's now return to that sort argument, which I was talking about before, but we skipped. So you can pass the sort parameter both to boundary cell data, boundary data, and the dist function. And basically what it does is that it's going to sort the values along the corresponding axis. And you can set sort either to X or to Y. So let's first, just to demonstrate why it might be needed, extract the boundary data for bottom wall. Oops. And we look at P. So as we can see, we start here from the right side. Okay, and then we slowly go down to, well, basically to 0. So the data as it is not sorted from little x to large X, it's the other way around. And generally you don't really have control over how the data is sorted, because if you have an unstructured grid, then it's going to be some unstructured, maybe some unstructured sorting in your boundary data. So if you want to sort it along a particular axis, you have to use sort. In general, you cannot rely on it already being sorted. So let's just do this sort X. Then if we look at B, we see that it's been sorted along X. Okay, the next function we're going to look at is TBL normals. And as you can expect, TBL normals gives us the normal vectors to a given boundary. So let's pass the case, and we pass bottom wall. So basically this edge, and we run it. Now, something we have to keep in mind is that the sorting here is as is. So we do not provide any sort here as we did for the boundary data. So it's going to be without any sorting, it's going to return the data as is for the edges. So as we remember, that means we're starting from the right side here. And then if we look at the data, first we have downward pointing normals, and then we have a small X component tuning in, which corresponds to this curvature. Then if we go further down, at some point we arrive to the flat part where it's just -1 again. And finally, minus on the X component and slowly towards just pointing down. So as expected, but the next function is tangents, and it's very similar. The only difference is that it's going to return the tangent vectors. So now we start from here, right? So the tangent is just directed towards X, and then we are going to get some positive Y component here, right? And then again, the flat surface just pointing to the right. And then finally here we get some sort of negative Y component as well. So this is more or less what you would expect. Now the normals are always outward pointing, but the tangents, it's a bit less intuitive, but basically the Z-axis and the outward normal and the tangents are supposed to form a how's it called? A right-handed triple, right? Because they're basically computed using cross products. Okay, as a final thing in this video, I want to give a concrete example of how the functionality that we've introduced can be used for some practical thing. And in particular, we're going to consider how to compute Y plus on the bottom wall of this periodic hill. Now let's quickly recall how y plus is computed. So y plus is the distance between the boundary and the first cell center, which is in the wall adjacent cell, so we call it y here, times the friction velocity, u tau, and divided by the viscosity, nu. And in turn, u tau itself is the square root of magnitude of the wall shear stress, tau wall, and that can be computed as the absolute value of the viscosity times the velocity gradient. So in this script, we basically go through unwrap these three lines into code. So the first line is just defining the viscosity, which happens to be this number. And then we are going to use the boundary cell data function to extract the values of velocity and the wall adjacent cells. And here we use the sort function to sort it along the x direction. And then V contains all the data, right? So we grab the field that we need, which is u mean. And then we're only going to grab the first two columns. Why? Because the z component is 0, right? So we don't need that. So we are going to get a 2D vector values. Now, what we want to do next is project the vectors that we got onto the tangential direction. The direction tangential to the wall, right? Because that is the velocity values that we want in order to compute the wall shear stress. And the little tricky thing here is if we just compute the tangents using the tbl.tangent function, we are not going to get them sorted along x, right? So we're not going to have the same ordering in the u and the tangents. So for that reason, there is another handy little function called tbl.sortIndices. And here you pass the case, the boundary, and the sorting axis, in this case x. And what that will give you is the indices that sort the values along the specified axis. Okay, so what that does is that means that we can compute the tangents using the tbl.tangents and then order them appropriately just by using the indices that tbl sort indices provide. So if we do that, both t and u are now equally ordered. So what remains is to compute the projection, and that basically we multiply component-wise and sum, so just take the dot product more or less. And given that, we are ready to compute the wall normal gradient, which we just approximate using a first order stencil. So what we do is we divide the velocity values by the distance to the wall, which we grab using tbl.dist. We pass the case, we pass the boundary, and again we sort them using the indices from the sort indices function, so that we are compatible with sorting in the u-tan variable. And then we're almost done. So now we can compute the tau wall, nu times du dy, and u tau also by definition. And then we can plot, we extract the x values and the u tau. And this is the result. So as you can see, the u tau is actually really low here, but one has to keep in mind that this is not a really good metric of mesh resolution perhaps for this flow, because it's separated here. So perhaps only in this region u tau makes sense to look at. But yeah, this was a very well-resolved simulation. Okay, so this I think concludes the video. There are some more things which we can look at in the package, more and more subtle. So stay tuned for future episodes. And thanks for this time, and see you later.